All right. Hey, everybody. So today we are doing topic 40, the first of three neural network study groups. So I'm going to touch on neural networks slightly different from what the curriculum goes through. For example, I'm actually going to talk about some of well, actually, the main thing is I'm going to talk about some of the appendix material next Tuesday in our third session, because I do think the appendix material, if you're working on the image classification project, you will get far more meaningful results if you were to use the appendix material. And I'm just going to provide you all with the code on how to do that, so that, it's a lot more seamless. So for our introduction to neural networks, we're going to figure out how they work. We're not going to go into much math because the math behind a neural network is very, very intense. I am going to send out, let me see, make sure that it is linked here. Here, I have two really, really great resources on the math of neural networks. One is from 3 Blue 1 Brown, and it talks about the math of backpropagation. Backpropagation is something that we're going to gloss over in a little bit. But it's basically how neural networks do their version of gradient descent. And then StatQuest. StatQuest, again, has really, really solid videos. They recently, in the last year, came out with a backpropagation series. I think it's like a 5-part video series on backpropagation, but their series on neural networks by itself, also very, very good. I will say that, like, I personally understood like kind of what was going on with neural networks as I was going through the program, like you all. But it was these videos that, like, just seeing things drawn out or represented in multiple different ways was super, super helpful. Cool. All right, so back to the top, what we're going to hit on today, we're going to talk about perceptrons. Now, perceptron, I believe, is a term that it used to not be in the curriculum explicitly, but I don't know if it is now. I believe it should be, but a perceptron is basically the building block of a neural network. A neural network is made up of a bunch of different perceptrons. So we're going to talk about what that individual building block looks like. Then we're going to scale it up to neural networks. Of course, we're going to do this like just conceptually on a very high level. Talk about what backpropagation is, and then we're going to build our first neural network on Google Colab. So Google Colab, I've shown some of you, and I think I showed it in like the last phase, but Google Colab is an online Jupyter notebook. So I'm going to show you all how I run code on a Google Colab notebook. So before I get into any of the technical material, I do want to show you all this cheat sheet that is on towards data science. And this is just a chart of different kinds of neural networks. So neural networks can exist in many, many different forms, which is why, well, I haven't said this yet, but you'll see that for this project, neural networks will be done on image classification, but neural networks can be used for pretty much any machine learning tasks that we've done before. Like, you can do any sort of classification, doesn't have to be images. It can be numerical. You can do it on your NLP data as well. You can do regression with a neural network. Tomorrow, I'll talk through some tweaks that you will have to make to a neural network to allow it to do regression. Last week, I talked about word embeddings. Word embeddings are actually created through a neural network process, as I like kind of glossed over last week. That is actually through autoencoders or any sort of encoder. So the process of encoding is taking something from one form and representing it as a series of numbers. That's why when creating word embeddings or any sort of word vectorization, you might see the word encoding come about, and this is the kind of neural network that does those processes. The neural networks that we're going to hit on, well, today we're going to talk about perceptrons, and we're also going to talk about feed-forward networks as well as deep feed-forward networks. That's what we're going to mainly talk about today. Other ones that we'll touch on during the next week, we're going to see very briefly, we're going to see RNNs and LSTMs. Sorry about the sirens, by the way. RNNs and LSTMs, these are the neural networks used for time series data. So I don't have any code examples, but I have a bunch of walkthroughs on how to implement these neural networks. So for those of you working on time series, I don't expect to see this for the phase 4 project. But if you're doing time series for your capstone, an RNN or an LSTM, great for including in a capstone. Other things that make use of RNNs and LSTMs, things like text generation or autocomplete, not autocomplete. Yeah, autocomplete, not autocorrect. But like when they're trying to predict what the next word is in your text, these are the neural networks that are used for that. Other ones that we'll talk about, convolutional neural networks. Where are those? Convolutional networks should be somewhere here. Here. Is it this one? Hold on. Where are my CNNs? Okay, deep convolutional network. Let's just say that this is a convolutional network. This will be the kind of network. This is actually the one that's in your appendix for images. So I'm going to talk about this one next week. Another one that's really cool to see is GANs. So GANs, if y'all are familiar with deepfake technology, any sort of deepfake is through a GAN, which is very cool. And the idea of that is it is adversarial. So you have like kind of two neural networks working against each other to try and like generate new images. And you have another neural network validating whether the image is accurate or not. So a lot of neural networks. SVMs, if you're using some sort of kernel trait, can also be classified as a neural network. So that's interesting. And yeah, the rest are just like kind of variations of each other. Any questions about these neural networks at this point? I think this gives us like a cool overview of like the different ways that neural networks can exist in the world. Cool. Yeah, I super apologize. I don't know what's going on out there with the sirens. Hope it's not too I hope it's not too what's the word? Disruptive. Okay. So anyways, when we move on to deep learning, I just found this meme on a Facebook group that when you get to deep learning, because of the level of predictive power that neural networks tend to have, you kind of overlook your other machine learning models. But we'll talk through some quick pros and cons of using deep learning neural networks over some of the scikit models that we talked about last phase. So first, some applications of neural networks. You can use neural networks for clustering. Neural networks, if you use images, you can do pattern recognition. When you're doing some sort of object detection, it actually kind of falls under the category of pattern recognition. So we'll talk about that more when we get to images next week. There's image recognition, which is CNN, convolutional neural networks. Time series forecasting, as I talked about before, recurrent neural networks, and audio, video, image generation, which are from GANs, which is the deepfake thing I was telling you all about before. Now, although you tend to get very high predictive power from neural networks, some downsides. They're good for prediction, bad for inference. From a neural network, you cannot do any sort of feature importance. You can't do coefficient analysis. You kind of have to treat it as a black box model where you have your inputs, you don't know what's going on. Yes, you get like weights and parameters and things like that, but they don't mean anything, even in the context of the neural network. So very, very bad for inference. Also highly computationally expensive. We're going to take a look to see a very, very simple neural network later on, and you'll see how many parameters it is tuning, especially in contrast to something like a logistic regression. Cool. So let's take a look at a perceptron. So the structure of a perceptron is actually exactly the same as the structure of logistic regression, although slightly different, and I'll outline those differences a bit. So here I have this diagram over here, and I'll explain this diagram with these bullet points. So this is a neural network, or a perceptron, or a single bit neural network. And this is for one row of data. So here we have a bunch of inputs. So we have M dimensions in our input data. So that means we have M features. So weights are determined through gradient descent. So when you have your inputs, you have these weights, and these are just some constant numbers that your inputs are, multiplied by. And then the bias term is our logistic regression intercept term. So every perceptron has an intercept term. So this is a bias that's also being added here. So everything is summed together, just like in like linear or logistic regression. You're doing like beta 1 times x1 plus beta 2 times x2 plus that intercept, sum it together. You pass that sum through an activation function. Now, when we talk about logistic regression, remember how we had that sigmoid function to force all of our values to be between 0 and 1. We're going to see more tomorrow that activation functions can have many different forms. You can have different activation functions for different purposes. But to simplify and to talk about it as a logistic regression, the activation function here is just taking whatever the sum that you got and applying that sigmoid function to force our values to be between 0 and 1. So after that, going through the activation function, as you know, logistic regression gives us some value that is between 0 and 1. between 0 and 1. And then we basically round it up or round it down to get our output of 0 or 1. And that's how classification is done. And so this is essentially exactly the same as what we did with logistic regression. If you remember when you had the, we didn't go very in depth with logistic regression, but if you remember our linear regression outputs when we had the table of coefficients, those coefficients are literally the weights. In that table, we also have our intercept term. All of those things are being added up in our linear regression or logistic regression equation. The only extra step between linear and logistic regression is we pass it through this activation function, and essentially, and at the end of that, we get our output. So the output here is our classification result. This is just a different or more neural network way of representing what is going on, because this is going to scale up in a bit. At this point, any questions about what we're doing here? All right, so for any one perceptron, the number of parameters that are being adjusted using gradient descent or backpropagation is the number of features. So here we have m features plus a bias term plus 1. So each perceptron, we're adjusting m plus 1 parameters. All right, I'm going to clear this. Cool. So the perceptron algorithm is all about learning the weights for inputs in order to draw a linear decision boundary that allows us to discriminate between two linearly separable classes. That's basically a long way of saying that if we have some data, this algorithm, which we did for logistic regression again, allows us to draw a decision boundary between our features. Now, what a perceptron does, as I mentioned before, it takes in some inputs, sums them up with weights, adds a bias, applies some activation function to produce an output. This I'll talk more in detail about tomorrow, but you can have different activation functions. And with logistic regression, we use a sigmoid activation function. Tomorrow we'll talk about in more detail some of the other ones. And basically, many perceptrons put together create a neural network. All right, any questions about what we've done here with this perceptron? All right, so basically to go from a single perceptron to a neural network, or the simplest neural network, is you're just going to combine a bunch of perceptrons together. So perceptrons by themselves are too linear. You have to go deeper. If you want to get some sort of decision boundary that is a lot more complex than a straight line, like something like this, for example, you're going to need much more perceptrons put together. So many perceptrons put together can look like this. And this is a single layer neural network. It's a single layer feed forward neural network. So if you remember over here, it is a feed forward neural network. And it's feed forward because the data is just going in one direction, meaning that your inputs start here, go into your layer of perceptrons, and then get output. Basically, it's a single direction where your data is flowing through. Now, this can be a little tricky to read. What this means is this is your input layer. And let's just say that this input layer has 3 nodes, meaning that we have 3 features, 3 X features that we're using for our classification or regression task. So here we have feature 1, feature 2, feature 3. Now, each of these features is going to be fed into 4 perceptrons in this diagram. So in this diagram, there are 4 different perceptrons, which is why you can see that every input goes into each perceptron. So from input number 1 goes into this one, goes into this one, goes into this one, and then also goes into this. And same for the other 2 features. So each of these perceptrons has its own different weights and biases that are going to be adjusted during backpropagation gradient descent so that you can end up with a nonlinear decision boundary at the end. Cool. Also, in addition to that, so actually, let me just go through these bullet points. Each node in the hidden layer works like a single perceptron. So each of this is a perceptron, and each node assigns different weights and biases to every row's inputs. Within each perceptron, you have an activation function. So there is an activation function happening within each perceptron. And then the outputs from the activation functions are aggregated to some output. And here you could even have a activation function at your output layer as well. It really does depend on your task. And we'll take a look at some more of that tomorrow, but we'll do a couple like simple examples today. So any questions about how this is being scaled? All right, all you have to know is coming out of each perceptron is some number, right? Like, let's say this is like 510. I'm making up numbers at this point, like 16. Let's say we have 72 here, and then like 40, I don't know, 48. These are just scalars that are coming out of the sum of weights and biases being passed through an activation function and then being aggregated. Also, they're being summed over here. And what happens here depends on what these numbers are supposed to do, and also depends on the task at hand. And again, for different purposes, you're going to have different output layers. All right. So some examples of activation functions, again, we're going to go through more of this tomorrow. Sigmoid, which is what we're using for our logistic regression. There is softmax. Softmax is actually one that's used for classification outputs. The most common activation functions that are being used currently are actually ReLU, which stands for rectified linear unit, as well as tanh, which is hyperbolic tangent. So both of these are actually the most commonly used activation functions. tanh is used more for recurrent neural networks. ReLU is used for most other things. But yeah, ReLU is basically non-rectified linear unit. Cool. So for output layer, softmax activation function is good for multi-class problems, and sigmoid if you have binary classification problems. All right. So activation functions, we're going to talk about more of that in detail tomorrow. So next, backpropagation. So backpropagation is the process of picking the optimal weights for any forward-feeding neural network. Backpropagation is the procedure that uses gradient descent to propagate error terms backwards. So this is required for any multi-layer perceptron or anything with multiple perceptrons, because in a linear logistic regression, you're pretty much just summing your weights, and that sum leads to your output. Whether something has to be done to that output, whether it is transformed with a sigmoid or not, is pretty much only dependent on one aggregated thing. When you have more than one perceptron at hand, you kind of need them to all optimize together. But because each of the weights and biases live within their own perceptron, you need to have a different way of optimizing for everything at the same time. And backpropagation is one way that does that. So backpropagation gets its name from the idea that errors are propagated backwards. And I know that's like kind of abstract, but basically what happens is once you take your data and you feed it into your entire neural network, let's say at the first pass, you have really, really awful prediction results. If you have really, really awful prediction results, it's going to see, all right, what should have been 0, maybe you got a value of 5. And it says, okay, I have an error of 5. How can I go move my error backwards? So with this difference of 5, it's going to say, all right, let's look at our last layer, the last layer that we had, and say, okay, how can we adjust such that this output of 0 can be closer to 5? And that idea of it's going to keep on looking back through all of the layers. And you can have many, many hidden layers as well. You can have outputs of perceptrons feeding into outputs of other perceptrons. So you're just going to keep looking back and say, hey, how can we do better based on the output that we got at the end? So that's where backpropagation gets its name from. The math of backpropagation is basically a lot of chain rule of calculus done at a very, very large scale. And again, the videos that I linked at the bottom, those are really, really good resources for explaining exactly how that works. So we don't have time to get into all of that. Cool. So something more about the mechanics of backpropagation. Oh, before that, any questions before I talk about the mechanics of backpropagation? All right. So gradient descent in neural networks are usually done in 2 layers. There are batches and then there are epochs. And these are things that you should tune. So neural networks are usually implemented with very, very large sets of data. Therefore, optimizing for speed in a lot of cases becomes a very big concern. So gradient descent can take a very, very long time to run if we use a single training example every time to update the weights and biases. Therefore, we usually use some sort of batch training. So imagine you have 1 million data points. If we don't do anything about training in batches, it's going to literally take each data point one at a time, look at its output, look back and say, all right, how do we adjust the weights for this specific data point, and do that one by one for every single data point that you have in your train set. So to mitigate that amount of time, we usually use some sort of batch processing. So first, for batch gradient descent, we are going to pass all of the training examples through the forward propagation stage before using back propagation to compute the weights and biases. So usually you can adjust your batch size, and we'll get more into that in a little bit. But in batch gradient descent, one way to do it is say, all right, if I have 1 million data points, let's look at all 1 million of my data points first and adjust the weights based off of an aggregation of the results of these million data points. So you can kind of like adjust your weights to accommodate for all of the data points that it's seen in the last million data points. You can also adjust these batch sizes. So if you have like 1 million data points, you can maybe do it like 1,000 at a time, or 10 at a time, or 10,000 at a time, depending on what you're trying to optimize for. So those are batches. And there are also epochs. And epochs is something that you also get to tune. And one epoch is when you're done passing all training examples through the forward propagation. So let's just say in 1 million data points, I decide to do batches of 1,000. So in 1 million data points, there's 1,000 batches of 1,000, right? Because 1,000 times 1,000 is 1 million. So one epoch, using those batches, means that you're going to give your data points 1,000 data points at a time, 1,000 times. And once it's seen all 1 million data points for one time, that is one epoch. Now, oftentimes when you are training, your first few data points versus training your last few data points, maybe your neural network is no longer optimized for your first few data points because a lot of adjustments have been made. So because of that, you might want to do multiple epochs. So doing 10 epochs, for example, is saying that, okay, your neural network is going to see each data point 10 times. So that means it's going to look at your data, it's going to look at 10 million data points in total. I know I shouldn't have picked big numbers, but any questions about the definition of batch and epoch? Cool, because that is very, very important terminology to understand. Okay, so there are different kinds of gradient descent, different kinds of like when is the back propagation process done. So there's stochastic gradient descent, and this is this is pretty much the standard one without using any batches, where it calculates the error and updates the weight after each training observation in the training set. So basically one single data point, that's when gradient descent is done. Batch gradient descent is it calculates error after each example is trained, but it's only updated after all observations have been trained. So it's the equivalent of saying that, all right, if I have 1 million data points, my batch size is 1 million as well. My weights will only be updated after seeing all 1 million. So typically what is done is you're doing some sort of mini batch gradient descent, where it's kind of like in between the two. Compromise between batch and stochastic gradient descent, it splits your training examples into mini batches, calculates the error, and then updates the weights after each iteration of the mini batches are done training. So what that means is if I have, that example of 1,000 batches of 1,000, the weights are going to be updated after each 1,000 data points. So in total, your weights, instead of being updated 1 million times or one time, it's going to be updated 1,000 times. All right. Any questions about this? We'll actually see this in action in just a little bit. All right. So one thing to also remember about the mechanics of how weights are being adjusted is random initialization. So when we feed node values forward through layers, we initialize the weights with random values and then the biases to be zeros. So each perceptron's initial weight has to be random values, and each intercept term should be 0. The intercept term actually doesn't matter as much, but the weights being random values is very important. We do not initialize the weights to be 0. Neither do we initialize each weight of each perceptron to be the same, because all the weights would end up being the same. And the point of a neural network is not for each perceptron to have the same value weights. Because if every perceptron had the same weights, it's pretty much like saying, all right, then why don't we just have a single perceptron and multiply everything by that number? So that's why weights are initialized with random values. And this is something that you don't have to do the initialization process on your own. Cool. So you also don't want very large initial weights because that will saturate the value of an activation function, causing the gradient of the activation function to be difficult. This will make more sense when we talk about stuff tomorrow. But in terms of the initialization, you don't really have to do anything with initializing your weights. Cool. So those are like the need to know things with regards to a neural network. And we're going to talk about implementing our neural network using Google Colab. So over here, I've linked, oops, let me reconnect this. I have linked the Google Colab notebook that I'm going through here. I'll also send it to the Slack channel a little bit later. So the library that we're going to be using for building a neural network is Keras. Keras is the default choice for beginner deep learners due to its user-friendly structure and easy implementation, and it is built on top of TensorFlow. So TensorFlow is actually the neural network library that was designed by Google, and Keras is something that is built to make TensorFlow easier to use. So it's kind of like the analogy I like to use is that Keras is to TensorFlow what Seaborn is to Matplotlib. So they're both building off of the same libraries. Keras just makes some things easier to use. As you get more of a sense of how to use and tune neural networks, and once you have a better idea of customizing your own neural networks, then you can move on to TensorFlow. But it's also very easy to switch from Keras to TensorFlow because the syntax is very, very similar. Cool. So let's take a look at our problem first, and then I'll come back to this. Also want to state that you don't have to always run neural networks through Google Colab. You can definitely run this on your own Jupyter notebook. Like for example, tomorrow, I'm going to be running the neural network through my own Jupyter notebook. I just want to show you all Google Colab. So Google Colab is really cool. I haven't formally talked about it yet, but there are a couple things to note. This is on the cloud. So it's pretty much like a Google Docs for I don't know, like a Jupyter notebook Google Doc thing. You can also send me Google Colab links. Those are actually very easy for me to see what you're running. So it's going to be very, very convenient. Some downsides though is with regards to data files, well, I guess /downside. Data files, because it's not on your local machine, you will have to upload any data onto your Google Drive. So it actually hooks up to your own Google Drive. And the way that you get it to do that is you use these 2 lines of code to mount your Colab notebook onto your Google Drive so you can access your CSV files. So actually, let me show you all how that works right now. So once I run this cell, oh, cool, it's already mounted. Usually what happens is it spits out a URL where you click, once you click onto the URL, you're brought to sign into your Google account. They'll give you some authorization code, just copy and paste that, and then you're in. So if you see over here, I hope it's not too messy. This is actually connected to my Google Drive. Oops. Oh, okay, let's try that again. So you can see what that looks like. All right, so here's my Google Drive. Mounting, and that is done. Okay, see, this comes up. It's going to sign in. Hopefully it doesn't have any passwords on there. Once I sign in, it is mounted to my Google Drive now, or in a little bit. Cool. Awesome. So once this is mounted, you can see that I have my Google Drive, and these are all of my Drive folders. Not important to see what those are right now. But mounted on my Drive folders, I can like CD into my files and access my data however I want. So that's there. Cool. Also, Google Colab runs, I think, Python 3.7, which is very stable. So if you have any issues with like weird dependencies, like for example, last week I was having really weird dependency problems because I upgraded my Python to 3.10. Google Colab is a very, very safe bet to run your code. Also, you can access it on different computers without having to worry about like Git and all that. Also talking about Git, since we're here, you can actually save a copy of this notebook in GitHub. They can actually automatically push not automatically, but you can actually directly push your changes from here onto GitHub if you want. All right. anything else? I don't think I have anything else. So a lot of the libraries already come pre-pip installed in Google Colab. If anything isn't installed, you can just do the same pip install, whatever. It works exactly the same way. So to demonstrate the neural network today, I'm just going to use this very, very simple data set. This data set is fairly small. Like typically, I wouldn't want to use a neural network for this data set because it's so small. It is only 768 rows, 9 columns, and so that means only 8 features. So this data set is already clean, so I'm just going to do my train test split, and feeding in the data that will be fed into the neural network will have 514 rows and 8 columns. Cool. So I've linked a bunch of the documentation here, but before I get into it, does anyone have any Google Colab related questions since we're here? Cool. All right, so there are some steps in specifying or building your neural network. So 4 steps to building your neural network models are: first, specify your architecture. How many layers do you want to have? How many nodes in your layers do you have? What activation functions do you want to use? And we'll get into more of these details tomorrow when we talk about tuning your neural networks. Next, there's a compile step. So in the compile step, this is where you set your cost function and details about how you want to optimize your problem. Learning rate optimizer, what metrics you want it to keep track of. That's what you'll do in the compile step. Next, you'll do your fit, and that's when the back propagation happens. And then you can make predictions. And we're going to go through all 4 of these steps in the Google Colab book. Okay, so with this very simple neural network, first we're going to do the architecture. So this architecture, first you instantiate the model by instantiating a sequential model. So I believe I'm very sure that all of the neural networks that are in our curriculum are all sequential models. Unless you're doing something fancy, like you're doing like a GAN, or you're doing something that isn't a feed forward network, it will pretty much always be a sequential model. So with a sequential model, you next have to add the layers of perceptrons. So over here, I'm adding a dense layer, and dense layer is the most basic layer that you have in a neural network. And these arguments, oh, actually, let me zoom in. Sorry, I realized this is quite small. So the 20 over here stands for the number of nodes, or the number of perceptrons that you have in that layer. So in this first layer, I'm saying, all right, I want there to be 20 perceptrons. For the very first layer, no matter what neural network you're doing, you always have to specify your input dimensions. And my input dimension here is 8 because I have 8 features. If you have 500 features, you put 500. If you're doing like NLP and you have 20,000 features, you can put 20,000 as well. Activation function, we'll talk about deciding on these more tomorrow. But for now, we'll just use ReLU because that is the most common activation function that's being used, usually also the one that performs the best in most scenarios. So we're just going to set the activation function to be ReLU. I actually believe that I want to say that the default is ReLU. Actually, let's find out. So Keras dense layer. So you look over here, dense layer, the activation function is actually none. That's interesting. I wonder what it is. Oh, okay. Never mind. I guess it's not ReLU, but anyways, you can see that you have to tell it how many units, which is the number of nodes, the activation function. You can add all of these other things if you want. We're going to talk more about, you can include like regularization, which is like if you have overfitting in your neural network, which actually happens very often, you can play around with these. But yeah. Cool. In this neural network, I just want to add another layer of perceptrons because I can. So usually with any dense neural network where, it's a neural network that has just dense layers, the number of nodes usually is in a funnel shape. So if I have, I usually start with the largest number of nodes and then slowly pare that down. I will say in choosing these number of perceptrons, it is fairly arbitrary. So that's why I just picked the number 12. So these are my 2 hidden layers. This is technically the input layer plus the first hidden layer. And then this is our second hidden layer. Then finally, this is something that you have to keep track of depending on what your task is. If you're doing binary classification, which is this problem that I'm doing over here, you need to have one output node where the activation is sigmoid, because sigmoid is what is used for binary classification just because the outputs have to be between 0 and 1. So that's why it's a 1 node output layer with a sigmoid activation. So this is our neural networks architecture. The next thing we're doing is the compile step. So the compile step, I'm telling it what loss function to look at. And loss function is actually what your neural network is optimizing for. And depending on what kind of neural network task you're doing, your loss function changes. So tomorrow I'll show you a list of like, okay, if you're doing regression, use this. If you're doing multi-class classification, use this. If you're doing binary, use this. So binary cross entropy is basically very similar to when we were doing decision trees. If y'all remember, decision trees had that entropy loss function, basically that. And when you see, we're actually going to run our neural network and we'll see some metrics. It is actually optimizing for whatever loss function you put over the metric. So you can actually give it a list of metrics. You can have it look at accuracy, recall, F1. But it's still going to optimize for the loss function. In terms of optimizer is basically how it does the gradient descent. We'll see more of these tomorrow again as well. But there are different kinds of optimizers. Atom is the name of an optimizer that is usually, it's usually the one that performs best as well. And in terms of metrics, we're just going to keep track of accuracy for now. Cool. So when I run this cell, it is basically creating my model. I wonder why it's taking so long. Okay, cool. This step is optional, but this is the model summary. And if you take a look at a model summary, it'll basically show you what your neural network is. So I have one dense layer, two dense layers, and one output dense layer. So this is a dense neural network. Interesting thing to take note of here. This neural network has 445 parameters to train. In contrast, if I were to take this data and feed it into a logistic regression, I would only have 9 parameters to adjust and train for, but this has 445. So just by specifying this fairly simple neural network architecture, you can see the amount of granularity that you can potentially achieve because there are so many parameters that you're adjusting for. Cool. Now that we've compiled this, again, this really doesn't do anything to your model. It just shows you what your model structure is. This is where you do the dot fit. Now, the dot fit is very important to remember. You should always save your fit step to a variable. Now, this is something that we didn't do in scikit-learn, but we're doing this for neural networks because the fit step actually does output pretty important things. And it actually outputs a dictionary of a bunch of training information. So when you do your dot fit, give it your X train, Y train, give it the number of epochs, basically the number of times you want your neural network to see your entire data or your entire training data. Verbose equal to 2, and you'll see why I do this because it has a cool output and it shows you when things are training, kind of has like a progress bar of sorts. I'm specifying my batch size here, so 100 per batch, and then I also can give it my validation data. Cool, so when I run this, it's gonna happen pretty fast. But you can see that my neural network is training, and it's going to train 50 epochs. Cool. When this is done, sorry, like it glitches out when it's my computer is lagging a little bit. You can see that it's training epoch per epoch. So it trains it 50 epochs, and you end up with an overall validation accuracy of 62%. What that means in context, of course, you're going to do your EDA, look at your class style and see what that means. But at this point, we have these values as our metrics. Now, it's something to note also, within each epoch, it's training like 6 out of 6. Now, this 6 out of 6 actually comes from our batch. So our batch size is 100. And if you remember, our training data, we had 514 data points. So it is 6 because it's doing 5 batches of 100 and then 1 batch of 14. That's why you have 6 out of 6 here. If your data was very, very complex and big, you'll actually see this number increase over time. It'll be like 1 out of 6, 2 out of 6, 3 out of 6. If you're doing like the image data, you probably will see that happen as well. So cool. Now that we've done this, it actually automatically just does your validation for you. And the idea here is over time, with more and more epochs that you add, your validation or your train and test accuracy will eventually go up. So I talked about why we have to save our training data as a variable. That's because you can actually get this information. Now you can feel free to take this matplotlib code, but this is the performance of our model so far. So you can see that this is our loss function on the left, and this is our train and test accuracy on the right. So because our model is optimizing for the loss function, usually you see a much more, what's the word? Like you kind of expect this kind of output in the loss function that over time, yeah, it gets better. Because it's not exactly optimizing for the metric accuracy, it's a little bit more unstable. But you can see here that loss event like does dip in within the first like 4 or 5 epochs, and then starts to plateau out. And then your train and test accuracy also, like I guess you can sort of say that it is gradually increasing. Maybe the increase gets a little bit slower over time. So what I'm going to do is I'm going to actually change this from 50 epochs to 300 epochs just to see what happens. And at this point, actually, before I do that, if you are changing the number of, you're changing something here, you actually have to rerun your compile step again. If you don't do that, actually, you might not want to do that depending on what you're doing. But if you don't do this, and if I just rerun the fit step, it's actually going to continue training from these first 50 epochs, which is really interesting. It's actually going to remember what these final weights were at epoch number 50, and then just keep running that on top of that. So it's just going to continue training rather than start training from scratch. But for this purpose, I want to start training from scratch. Cool. Any questions while this runs? It's going to be fairly quick, but any questions at this point?
So kind of piggybacking off of what you just said. So if we, I guess, spend like an hour training a neural network and then just stop it and then continue the next day, it kind of still works the same. Okay.
Yeah. So as long as your kernel doesn't die, or as long as you don't, as long as you don't stop your kernel from running, the weights will be saved. I believe, I don't know, no, this is going to be in next week's notebook, but in next week's notebook, I actually had some code on how you can actually save your weights. So if you wanted to continue training your model elsewhere, you can do that too. Cool. Anything else? You're welcome.
So if you is it correct to say that like if you adjust your batch size and your epoch, that would affect like whether you increase it or decrease it, it'll affect the accuracy?
Yeah, usually adjusting the number of epochs has a larger impact on your accuracy. Like for example, I just change it to 300 epochs. So instead of just seeing the data 50 times, it's actually seeing all my data 300 times. If I look at this graph, and if you remember, I think before it was, I want to say 62. Now we have a validation of 74. So by letting it train 250 more epochs, it has reached an accuracy of 74. I mean, it's a little bit unstable, and of course, more can be done about that. We'll talk about that more tomorrow or next week. I forget when exactly we're going to talk about this specific thing. But yeah, usually the more epochs you get, definitely your training loss will get lower and lower. Your weights will keep adjusting such that you tend to get better results or more accurate results with your train set. The more epochs you have.
Thank you.
You're welcome. So several things to note. You can see that the loss has started to really plateau out here. And with my train and test accuracy, you could also argue that it's starting to plateau out. Of course, I could let this train for up to 1,000 and see where it ends up going. But let's just say it really starts to flatten out. So the test accuracy is this blue line. So let's just say that, and let me just switch this color to something blue. So let's just say that this plateaus out like that. Okay, it's bad drawing, but you get my point. So if you're seeing that my test accuracy pretty much like tops out somewhere over here, that's basically saying that there's really no added benefit of training it an extra like almost 200 epochs. So when you see something like this, you can be like, all right, why am I spending all of this additional computational power to train an extra like 175 epochs when the test accuracy doesn't go up by very much? And this is actually something that in big companies where you really care about like your resource allocation, like how much computational power you're using, because sometimes you're paying for it in the cloud or you're paying for your like server space and so on and so forth. This is something that you would actually look out for and say, all right, this marginal increase in my accuracy is not worth however much this costs. So this is something to take into account as well. I'm gonna show you all something else tomorrow. Yeah, I'm gonna show you all that tomorrow, where you can actually tell your neural network, okay, I'm gonna train it for 1,000 epochs. However, if for about 10 epochs in a row, let's just say, my accuracy doesn't go up anymore, just cut it off there. So that's actually something really cool that you can implement within your neural network. We'll talk about that tomorrow. Any questions about interpreting this? Cool. It's not surprising that in terms of our accuracy over here, you can see that our training accuracy is always a little bit higher than our test accuracy. In this example, it seems to be only like not too far off. Let me scroll up a little bit to see. Yeah, 75 and 74, not too far off. I can make this kind of match back up. There we go. 74, 75, so not too bad in terms of like overfitting. But it is actually fairly common to see overfitting start to occur with your neural networks. And by the way, this x-axis is the number of epochs. So if I see that for whatever reason that, I mean, similar to it plateauing out, if I see that my lines start to diverge, like maybe, okay, my testing accuracy goes like this, and then actually starts to get worse due to overfitting, while your training accuracy continues to go all the way up, that's a sign of overfitting. You could say, okay, I want to stop training over here. Typically for the loss function, because the loss is exactly what the neural network is optimizing for, at least the training loss will always be decreasing. Maybe it like plateaus out and decreases by like a very, very little bit, is always decreasing because that's what the gradient descent is looking to decrease. So we look at these like losses over here. I mean, it's a little bit unstable because at this point it's kind of plateauing out, but generally it is working on decreasing the loss. And in terms of like the testing loss could be a little bit more fluctuating, but you can see that your training loss, and loss is a bad thing, so you always want less of it. Your training loss is always a little bit lower than your test loss. All right. So finally, just really quick, you can do dot predict with your neural network. So you can do a dot predict on my X test, and I get my results over here. Because this is a classification problem, you want to like round it off. I think it's predict or predict classes. Is that the one? I forget what the exact one. There's one function that gives you like a 0 and a 1, because your dot predict gives you the sigmoid output. So you actually want to round these numbers off as you see fit. All right, that's all for today. Does anyone have any questions about any of the things that we've covered today? All right, so tomorrow, even though I know that tomorrow, like topic 41 is called deep neural networks, I believe, we're going to talk more about tuning neural networks and all of the different things that we didn't really get to talk about today. So we're going to talk about like a lot of little details. We're going to talk about like activation functions, what nodes and layers are, different loss functions, optimizers, and we're going to start talking about image classification as well. We're going to talk about convolutional layers, which is going to be very, very important if you're doing the image classification project. Cool. Any questions before we end off? By the way, don't forget to add your stand up to the thread, and also on the poll, put down what project you're working on so that I can, keep track as an aggregate. All right, if there are no questions, I will see you all tomorrow. You all have a good rest of your day, night, and any questions as usual, Slack me. Bye, everybody.
Bye-bye. Thank you.
Bye, guys. Have a great night.
Bye.